Now we're going to look at exponential functions. Now you may have heard the phrase in the past, exponential growth. Something is growing exponentially. Well, exactly what does that mean? Well, that's what we want to notice here. So let's suppose we've got some values for x, and what I want to do is I want to kind of go point back to what we know about linear functions and then show you, make a connection to exponential functions. So let's think about the function 2x, and we're going to compare that to 2 to the x. Now this right here, this 2 to the x, that's an exponential function. This over here, 2x, is a linear function. Now look at the difference in these values. For 2x, every time we put an x in, it just doubles. And notice as we go from one value of x to the next, so if we go from 0 to 1, we increase by 2. If we go from 1 to 2, we increase by 2. Notice every time with this linear function, as we increment 1 on the x, we increment 2 on the y's for this particular function. So it goes 8, 10, 12, 14, and so forth. So there's a common difference. That's a linear function. Now notice with the exponential function, it's a little bit different. Notice that as we go along here, to get to the next term, we're multiplying by 2. So 2 times 1 is 2, times 2 is 4, times 2 is 8, times 2 is 16, and so forth. And what we have here with these exponential values is we have a common ratio. So if we take one term, if x is incremented by 1 each time, notice, if we take a term and divide it by its previous term, we get 2 on this particular function. So 8 divided by 4 is 2. Maybe 32 divided by 16 is 2. Yeah, 128 divided by 64. So with exponential functions, if you just set your x's to increment a certain amount, the ratio of the y's, 1y divided by its previous, is always going to be the same. And in this case, we were incrementing x to be 1. 1, 2, 3, and so forth. And notice all the common ratios here are 2. 32 divided by 16, 16 divided by 8, 8 divided by 4, they're all 2. Now, we didn't have to increment by 1. We could have incremented x by 2, but here's, when we increment by 1. So down here we've got 2 to the k, and up here 2 to the k plus 1. So we've got the kth term and the kth plus first term, and we get a common ratio of 2. You can work out the algebra here, but let's suppose we don't increment x by 1. Let's suppose we go from 2 to 8, notice. So x goes from 1 to 3. So we take this x equals 1 term and the x equals 3 term and divide. 8 divided by 2, that's 4. Let's try another one. 64 divided by 16. Notice I skipped this middle term. Get a common ratio of 4 there. So when we went from 4 to 6, x goes up by 2, and we still get a common ratio. It's not 2 like it was when we incremented x by 1s, but this is the property of exponential functions. This is what makes it an exponential function. So if we take the kth term and then the k plus second term, right? Notice in this case we're always going to get 4. Now that's because my exponential function was 2 to the x. I didn't have to have 2 to the x. I could have 3 to the x and so forth. And we wouldn't have a common ratio of 2. But for exponential functions, you have a common ratio is the point. It doesn't have to be 2. But we say this is the base. This 2 is the base. 2 to the x power. 2 is the base. Now, let's just see how these exponential functions might be used to model, some kind of situation that we observe. Let's look at this really simplistic situation here where you have this virus, and everyone that has the virus, at the end of each month, they give it to exactly 2 people. No more, no less. Exactly 2 people. Well, so let's see how this would look. Let's make a table here. When we start off, let's suppose we have 3 people. Well, that's how many people have this virus the first month. But at the end of the month, you give every one of these 3 people, each of these 3 people gives the virus to 2 more people. So the number of people that have the virus now is 3 times 2. In other words, 6. Now, Another month goes by, and each of these people give it to 2 more people. So these times 2. See that? And we get 3 times 2 squared. Then another month goes by, and now these people, this many people, each one of these gives it to 2. So you can see what's happening here. And finally, if we say, well, what about the kth month? Well, the kth month, this is how many people have the virus. 3 times 2 to the k. And we could say, okay, I can write a little formula for that. F of n equals 3 times 2 to the n. Now, with this example, I used n, and it was kind of discrete. I went from n equals 1, 2, 3, and so forth, and I left off all the numbers in between, 3.25 and all that. But in general, when we're using exponential function, we'll put in, all those values. We're going to say the domain is all real numbers on these exponential functions. Now, so let's just take a look at these values real quick. Once again, when we have values for x, and then we have 2 to the x, we can put in 0. Notice, if I put in 0, I get 2 to the 0, which is 1. If I put in 1, I get 2 to the first. If I put in 2, I get 2 to the second. 3, I get 2 to the third. Now, notice what's happening here. As x is getting larger and larger and larger, the function value is getting larger and larger and larger. In fact, it's going to infinity, right? So if I put in x is 5,000, I would have 2 to the 5,000th power. So this exponential function, as x is going to infinity, it's just blowing up. It's growing without bounds. Now, what happens, though, if I put in negative values for x? Well, if I put in -1, I get 2 to the -1, which is 1 over 2, which is 1/2. So notice, now I'm going in the negative direction. What if I put in a -2? Well, I get 2 to the -2. That's like 1 over 2 squared, right? Because it's a negative exponent. I get 1/4. What about -3? I get 1/8. -4, I get 1/16. So here's what we note here. As x is going to negative infinity, if it's going to in the negative direction, this function is getting smaller and smaller and smaller output. It's getting smaller and smaller outputs. In fact, it's going to 0. Now notice those outputs will never be 0. They're just getting very, very small. So if I put in 1,000 for -1,000 for x, I would get 1 over 2 to the 1,000th power, which is very close to 0. But notice, there's no value I can put in for x to make this thing actually equal 0. It's just getting close to 0, asymptotically. It's asymptotic to the x-axis. So look, here's what the graphs look like. Here's a 2 to the x right here. See how it grows? Okay. As you go to the right, as x grows, this graph is growing very quickly, going to infinity. But as you go to the left, notice it's getting closer and closer to 0. It's getting asymptotic to this x-axis here as x goes to negative infinity. Now, we could have other exponential functions like 3 to the x. Its basic shape is the same. It's going to be steeper, though, over here, notice. And 4 to the x. If we had 5 to the x, it'd be a little steeper. But notice they all cross here at 1, at 0, 1. Okay? So this is just how these exponential functions behave if we have a base bigger than 1. And I'm assuming here a is positive. Okay, I'm assuming here a is positive because if a were negative, it would turn the graph upside down. So we're just assuming a is positive. I probably should have put that in here, but if the base is bigger than 1, this is the type of growth that you see, like this. Okay, now let's leave exponential growth for a minute and look at exponential decay. Let's suppose that you have a town, and here's what happens. The population is 96%, and each month, half the people leave. Okay, let's see. I had to go back and read it. So let's suppose you've got this population of 96, and at the end of each month, half the population just walk off. They leave the town. So let's see what this would look like. we start off with a population of 96. And then, after 1 month, how many do you have left? Well, 1/2 of the 96. That's what you have left, 1/2 of the 96. Okay? Then, what about after that? After 2 months? Well, you've got, this is the population now, and you have half of those. Okay, so now you only have half of those. So this is 96 times 1/2 squared. So each time your population is being cut in half. That's what's happening. You have half the population leaving. What about after 3 months? Well, you have 96. You have this times 1/2 squared. That's the population for, month 2. And then you're going to take half of that. So in fact, you could say, well, okay, the kth month, this is the population of my town right here. Okay, right there, 96 times 1/2 k. Now, of course, a model for that could be this, right? And this is an example of an exponential decay. Now, just like we did for exponential growth, let's see if we can get an idea about what the graph would look like for an exponential decay model. So let's consider a table here. We put in some x values, 0. Now notice, if x is 0, 1/2 to the 0 is 1. So just like with the exponential growth, for exponential decay, it has a y-intercept of 0, 1. Now, what if we put in a 1? Well, we get 1/2 to the 1, which is 1/2. What about a 2? 1/2 squared, which is 1/4. If we put in a 3, 1/2 cubed, which is 1/8. Now, dig what's going on here. As x is going to infinity, this function is getting smaller and smaller outputs. It's not like with the growth. Remember, with exponential growth, as x goes to infinity, the outputs go to infinity. However, with the exponential decay, as x goes to infinity, the outputs get smaller and smaller and smaller and tend towards 0. So this function is becoming asymptotic to the x-axis when x goes to infinity. Now let's see what happens when x goes to negative infinity. Okay, when x is -1, we have 1/2 to the -1 power. Well, that just flips the fraction and we get 2. 1/2 to the -1 is 2. Okay, 1/2 to the -2 is 4. 1/2 to the -3 is 8. 1/2 to the -4 is 16. So now we see what happens when x is going to negative infinity for the exponential decay. Your function is going off to infinity. Okay, so as x goes to negative infinity, f of x goes to infinity. So here's an example of exponential decay. Notice we've got the 1/2 to the x, 1/3 to the x, 1/4 to the x. And in general, we could say this, that when your base is between 0 and 1, not including 0 and 1, you have exponential decay. And it would be, depending on what the base is, determines the steepness here. Okay, now let's look at, let's just take note of something here. Whenever you have exponential growth, in other words, if you have a model like this, remember we're assuming a is positive, just some fixed number, positive number. And in fact, for simplicity's sake, let's just say a is 1. I regret putting a here, but I just want it to have the general exponential model. But notice this is going to be the basic shape of the graph for exponential growth. Now the basic shape for exponential decay is going to look like this. Okay. Now I have here the y-intercept is 1, but if a is something else besides 1, that's going to affect this y-intercept. But anyway, these are the basic shapes of this. Okay, I'm regretting putting that a there because I just want to show you the basic shape, the basic behavior of exponential growth and exponential decay. Okay, now these are what the graphs look like. We have these two basic graphs, growth and decay. So let's suppose we have this function and we want to figure out, okay, I've got this parent function. This is an exponential function. So we're kind of adding exponential functions to our list of parent functions that we know. This, we want to sketch this graph. Now, we have to determine, first of all, the shape. Is it exponential growth or exponential decay? See? Now, the base is 2. That's bigger than 1, so it's this one. It's going to be exponential growth. Okay? So this is the function we're dealing with here. Now, notice what we can do is we can find the y-intercept. The y-intercept is going to be, we just put in a 0 for the x, like always, and we get 5. So this graph, we know, crosses the y-axis at y equals 5. Now, remember, these exponential functions have horizontal asymptotes, and normally, for just 2 to the x, that horizontal asymptote would be the x-axis. But what's happened here is we've shifted up 3. We've shifted up 3 units. So the whole graph is raised up 3 units. So if the x-axis, y equals 0, was the horizontal asymptote, the horizontal asymptote now would be 3, right? Because this is a vertical shift, this number here on the end. So now notice what we have. We have the y-intercept, we have the horizontal asymptote, and now we can get a better idea about what this graph actually looks like. Notice, here's the horizontal asymptote, here's the y-intercept, and there we have it. We've sketched that graph. Now, one more thing I want to talk about here. Just there is this number e that it's like pi in that it's an irrational number. There's no detectable pattern. You know, it goes on and on forever. Very important number, but it's the natural base, and we just denote it by e. You know, and its first few digits is 2.7182818284559, so forth. It goes on forever. But notice its base, this is bigger than 1, so it's an exponential growth function. So e to the x is an exponential growth model. But you're going to see e a lot, so we need to just be sure and take note of what that is.